of a target exploration problem, where you get to see here the autonomous deployment of a quadrotor that is moving autonomously to thoroughly scan an area, searching for potential targets. So this is the first phase of a project where we are trying to integrate now visual target detection with computer vision collaborators. And resilient network control is another of our area, another area that we are working on, that has to do with how we can achieve collective behaviors for our multi-agent systems safely in the presence of adversaries. So if time permits, I'll discuss a little bit about the resilience aspect, but here is an overview of our architecture. So, as I mentioned, we focus on multi-agent systems, meaning you have a set of agents, could be robots, UAVs, heterogeneous vehicles, whatever. They have to achieve a collective behavior. They have to achieve a set of goal states, and they have to stay away from unsafe states in the environment. Could be the physical obstacles, could be unsafe areas that they shouldn't be entering, and so on. So what we are trying to develop here is essentially the control and estimation for each one of those agents. So if we want to see things in a block diagram, this would start giving us more context here about what we are trying to accomplish. So we want to take into account the fact that you're typically operating in an environment where you might be subject to attacks, either physical attacks, so physical adversaries. There might be agents that might want to crash with you, or cyber attacks. So there might be agents that might try to exert malicious information to the network. So we are interested in how we should develop, how we should design the structure, the topology of the network, such that communications can be cast secure. Now, what do I mean by secure? By secure, I mean that you can develop then an algorithm to process the information that is being shared between the agents, such that this information that the agents are sharing with each other and with which they have to make decisions through communication or sensing. Sensors can also be fraud or just faulty. So with all this available information that is not the absolute truth, it's not correct, each one of the agents will have to play a filtering mechanism to reconstruct its own states and the states of the others, and an estimate of where they should go and how they should go there. Because essentially this is the information that you feed back in your system when it comes to maintaining safety, okay? So you use this information in a safety critical control algorithm, and this is where I'm going to focus most of the talk today. Because this is the overall block diagram, if you wish, of the problems that we want to address in this area of safety and resilience for multi-agent systems. Okay, so time permitting, I will try to make some connections of multi-agent safety critical control with resilience towards the end of my talk. And let me get now into the actual problem that I will be talking about today. So the work has been motivated from this type of spatiotemporal control synthesis and motion planning in robotics, primarily, where in the past couple of years, people have been very interested in how to encode the mission synthesis for objectives that go beyond the go from point to point planning and control problems, okay? So people have developed lots of methods that are related to how we can encode missions using tools from formal methods, like from using linear temporal logic specifications, and more recently, signal temporal logic specifications, since they are more amenable to encoding temporal aspects also of your constraints. So they are more amenable to dynamical systems. And at the end, when it comes to problems such that I have one robot or many robots that have to do tasks like They have to always evolve in the free space, avoiding obstacles, and maybe eventually visit area, let's say P1, while always avoiding area P2, and so on. So you can have representations of these missions through this type of specifications, and at the end, you end up having problems of safety, in the sense of always system trajectories staying within, let's say, a safe set S, and maybe reachability of eventually trajectory starting from a set S1 would have to converge to set S2, and from there to a set S3, and so on. So, so safety has been well treated as a problem of how to essentially, can be cast as a problem of set invariance. And performance, in our terminology, is a problem of set attractivity. Okay, so you want to reach from set 1, let's say, to set S2 within a specified time. And this is the new element that we are adding into this picture. So not only you want to reach, but you want to make sure that you will not reach later than a given time, because this time is a constraint in your mission as well. Okay. With all the constraints also in the picture when it comes to inputs, other state constraints, dynamics, other agents, the question is how we can cast now a control framework for the synthesis of the controllers that can realize this type of spatiotemporal missions starting from a single agent formulation, where you use the notion of control barrier functions in order to prescribe the safe level sets of this function, such that the trajectories will always be confined within the safe set. And as we move towards the spatiotemporal aspect and multi-agent systems, the question is how you can take these control barrier functions, add them time specifications, and take into account also your neighbor agents, such that you can design a timed control barrier function for each one of your agents and eventually synthesize it in a big multi-agent system. Okay? So this is some of the ongoing work in my group. I will be mostly talking about this part here. We are extending towards multi-agent system. This is ongoing work. Okay, so as I said, safety and performance in terms of specified time are our two main objectives, and the problem is how we can synthesize control barrier functions that encode this type of constraints, okay, the spatiotemporal constraints. So the approach that we have followed is to incorporate tools from finite time and fixed time stability, okay? And I will define what we mean by finite time and fixed time stability more formally in the next slides. Briefly speaking, finite time compared to asymptotic stability notion means that convergence to, let's say, the equilibrium or a desired destination happens, as the word says, in finite time, not asymptotically with time, but you can hit the origin, let's say, within a finite time, which, however, depends on the initial condition that you started from. Okay? So this is a notion that has been developed in the literature since a while, and more recently, people started thinking whether there can be stronger notions of finite time stability, and they defined what is called fixed time stability, where essentially the time of convergence is fixed and essentially is independent of the initial condition in the sense that it is upper bounded by a bound that does not depend on the initial condition, okay? But cannot be predefined by the user, okay? Prescribed time is an even stronger notion where the time of convergence can be arbitrarily defined by the user. So we are making use of these notions here, and we have been developing some tools that can be used either for analysis of finite time stability of switched and hybrid systems and synthesis when it comes to using control barrier functions and quadratic programs, properly defined quadratic programs that encode finite time or fixed time stability. Yeah, of course.
I'm guessing the finite time stability could be a global property as well, right? Doesn't have to be local.
Yes.
And what would fixed time and prescribed time? Is it possible to have global property for fixed and prescribed?
Yes, you can have, assuming that, of course, the system has a specific structure. We will see there are very nice Lyapunov characterizations on those. So let me go to the next slide, which hopefully will give you the explicit answer to your question. So, okay, so this is the outline of my talk today. I will give you the overview of how people have defined finite time and fixed time stability before, and how we define our prescribed time control barrier functions based on those notions, and the quadratic programming formulation that we propose in order to solve this type of problems. And we have done also, as I said, work that is related to analysis and the other type of prescribed time control designs that I will not have the time to discuss, but I'm happy to send you papers or discuss afterwards offline. And time permitting, we will see some of the connections with resilience in our ongoing work. Okay? So, what do we mean by finite time stability? So, as I said, in contrast to asymptotic convergence or even exponential convergence, which is convergence as t tends to infinity, finite time encodes that you have to hit the origin or a desired set point, as described here, within some time, some finite time t. That comes, of course, with the peculiarity that essentially this, and in fact people have proved that a necessary condition for having finite time convergence is that your system dynamics is non-Lipschitz at the origin, okay? So you lose here the standard formulations where you start with systems that are locally Lipschitz and so on. So here we consider just an f, which is a continuous function, under the assumption that the solution of the system exists and is unique. What is nice is that people have already formulated the Lyapunov-based characterization of finite time stability. And if you can find a positive definite function v, a Lyapunov function candidate that satisfies now this condition when it comes to the time derivative, whereas you see this vita term is between 0 and 1, then the origin is finite time stable with settling time that satisfies here this upper bound. Okay, so as you see, this bound here depends on the initial condition. And this is work by Butt and Bernstein back from the 2000. Okay, okay, yeah, sorry. Okay, so as I said, people have kept looking into these properties and developed, Polyakov and his co-authors more recently developed the notion of fixed time stability and gave a Lyapunov-based characterization. So for the same type of system here, you're going to have a fixed time stable equilibrium if you can find a positive definite function v for this system here, for which the time derivative satisfies this condition here. And you get to see that you have one term that behaves as the finite time stability term from before, and another term that behaves according to the usual asymptotic stability. Okay? So, and you get to see it is proved that the origin of the system is fixed time stable, and the continuous and the settling time function satisfies now this bound here. So the time to converge t is upper bounded by this quantity, which these parameters here depend on the system, on whether you can find this Lyapunov function, and do not depend on the initial condition. Okay? So, so we became aware of the existence of those Lyapunov-based results, and that was the main motivation. Oh, sorry, my graphics have not been coordinated well. Okay, so here is the finite time convergence concept that you hit in a finite time that grows with the initial condition, and here would be the concept of fixed time converging no later than that would be your tau, let's call it tau bar, the right-hand side of this equation here, that would be your tau bar. Okay, so we became aware of those results, and the initial motivation was that when you have switched systems and when it comes to the stability of switched systems and hybrid systems, there are so many nice, beautiful results out there in the literature that depend on multiple Lyapunoy functions and common Lyapunoy functions. So we wanted to use now these characterizations with Lyapunov stability, these Lyapunov-based characterizations of finite-time stability to encode that not only we want to converge, but we want to converge within some finite time, okay? So that would be the tools that we are using for convergence. Making here a quick review of the main results when it comes to barrier functions for safety. So Ames and his co-authors very recently published a nice paper where they summarize all these concepts of reciprocal barrier functions when you have a safe set or a set of state constraints under which conditions you can call a function reciprocal barrier function for this set. So essentially the idea is that you want to make sure that on the boundary of the set, the closed loop vector field would always point you into the interior of the set, which is nothing but the representation of Nagumo's theorem for this class of sets and this class of functions. So if you can find such a reciprocal barrier function for a set of state constraints, then you can prove that the set is going to be, the interior of the set is going to be forward invariant. Let me move a little bit quickly through those slides because I'm pretty sure that you are very aware of those results. Similarly, the zeroing barrier functions are defined similarly or only to reciprocal ones. The difference is that they are defined to be 0 on the boundary. And with a characterization for set invariance with these functions for systems without control inputs, the question is, okay, if we have now systems with control inputs, like systems that are control affine, nonlinear and control affine, then what are the characterizations for controlled invariance of the set? And you can use the notions of these reciprocal or zeroing barrier functions along with the main idea of a control Lyapunoy function, which says that if you can make the time derivative, that would be like your B dot here, right, along the system trajectories, if you can find the control input such that this B dot here is rendered smaller or equal than 0, then essentially you can have a controller that renders the closed loop system, the safe set, positively invariant under this choice of the control input, right? So similarly for the case of a zeroing control barrier function, here you use the supremum because you want the H dot to be always positive or non-negative. Okay, so up to that point, I'm just reviewing here basic tools in the related literature. And the main formalization of, let's say, a prototypical problem would be if you consider now together safety constraints in terms of, let's say, a reciprocal barrier function. So you might have a problem where you have a set of state constraints that should never be violated. And at the same time, you might have an additional objective, which would be a performance objective, such that I want my trajectories to converge towards a desired set point. Then you can formulate a quadratic program that computes that's trying to find the minimum control input, the minimum norm control input, such that these constraints here are met. The safety constraints. This would be the safety constraints, and this would be the convergence constraints towards the desired set point, okay? And the challenge comes into the picture when these two objectives are conflicting because you might want to stay safe and go somewhere, but this might not be a consistent, but these might not be consistent objectives. So the authors here decide to, so solution might not even exist for the concurrent satisfaction of these objectives. What can you do in that case is to design to relax one of the objectives. In that case here, it's the convergence objective in the control Lyapunoy function formulation with this slack variable delta here, okay? So, and people have used this type of control barrier functions formulations for many very interesting, challenging applications, bipedal robots, flying quadrotors, and so on. And let me go back now to our original problem, which is how we can put together safety critical and time critical constraints in this control synthesis and formulate a proper QP in order to solve for these spatiotemporal constraints, okay? So I'm just repeating here the setup that we have. And the idea with all these tools that have been already developed in the literature for us is now seems, I think, rather simple. How can we synthesize control barrier functions if we are given a set of spatiotemporal specifications? Then the natural question, the natural answer, I think, would be, why don't you try to formulate a quadratic program that encodes safety, as people have already encoded it, and convergence within some given time for reaching your set within the time specifications that you have in your problem. Okay, so let's see how this QP-based approach would look like. So we are considering the class of systems that are affine in control, nonlinear systems that are affine in control. And for the sake of having a, well, it could be simplified as a, or, so we consider the case where we have a set of state constraints, S, defined as wherever some functions here take non-positive values. And we consider also these sets here Si, let's call that we have a finite number of them, where with the objective of making sure that we start always from a point that is within the interior of the safe set, and with the objective of finding control inputs that are going to make our trajectories always stay within the safe set and move from set I to set I plus 1, okay, within a given time. So, and we're going to assume for now that there exist some time intervals, Ti plus 1, such that the length of this time interval is greater than a time T bar, okay? And we're going to see how this time T bar gets into the play in order to ensure the feasibility of our problem. So we have also control inputs in this box type form. And as I said, the problem is how to find a feasible control input such that we have set invariants for the trajectories of the system and also attractivity of set Si plus 1 from the trajectories lying in the set Si. Okay, so what is the new element that we need in order to define this type of, to solve this problem? So we are going to define here that a continuously differentiable function V, so we want essentially a function V that satisfies these fixed time convergence properties that I was describing earlier, okay? So we are going to define here that if we can find that the continuously differentiable function V such with parameters A1, A2, B1, B2, and for some tau bar here that I will again explain how it gets into the picture. And this function is positive definite with respect to a closed set meaning that it is, let's say, positive outside that set and 0 on the boundary of the set, also into the interior of the set. So you can see that the set could boil down to just a point, the origin, or in general as a goal set of states. So we want this function to be positive definite within this set. And what else do we want? We want the time derivative of this function. This is nothing but essentially v dot here under the selection of some control input to satisfy, not surprisingly, this is the fixed time convergence derivative that comes with a fixed time stability characterization, okay? So if you can find, essentially, these parameters here, such that these conditions here hold for your candidate Lyapunoy function, then this function is called the prescribed time control Lyapunoy function with respect to this set S. What does that mean? That means that for this tau bar, look at that now, this tau bar essentially is lower bounded by the uniform bound of fixed time stability, okay? So what we say here is that if you can choose, and again, you do not choose it arbitrarily, so the prescribed time is probably not the very best term to use. It's a user, so if the user can define a time t bar such that it is lower bounded by this fixed time convergence, fixed time settling time ultimate bound given by these parameters, okay? And if your function satisfies these conditions, then essentially that means that you can hit the set S, starting outside the set S, no later than this t bar time. So you have encoded this temporal constraint in your Lyapunoy function in a Lyapunoy function. So what does that mean? That means that if all these things happen to hold, okay, at the same time, means that you have a system and you have temporal specifications and you have spatial, or you have essentially state and time constraints such that all these conditions here hold at the same time. And what are those conditions? What do we pose here? We pose that you can pick a user-defined time that is lower bounded by the fixed time convergence, the fixed time settling time, in order to have this convergence before the user-defined time. And if you can have safety, forward invariance of the safe set encoded through a control barrier function condition, and you can have forward invariance for your sets Si to make sure that once you get into set Si, you will not escape Si unless you choose a different controller. And you have here also the fixed time convergence condition for making sure that trajectories will, from Si, will hit Si plus 1 within this fixed time that you have set essentially here. Then essentially you have a control input, okay, that solves this problem 1. Means that you, yep.
So when you formulate this as a QP, the C3 constraint has to be replaced each time you...
Yes, when you use for this type of sequential, you will have, once you hit S2, then essentially the objective becomes, I want to go now to the next set.
And I may not be, the control effort may not be continuous?
No. Well, we, under certain assumptions, not for this formulation, we can show that the control input can be continuous, but not necessarily for this formulation here. It's our ongoing work. I'll show you. It's a good point. So here we essentially say that if all these happen to be met, then we are good. But obviously, this is not always the case, right? So in our first, and this is earlier work of ours. This is the paper that appeared in last CDC. So for the case that everything can be met without needing to relax any of our constraints, this is the QP that would be formulated, as you said. So we want to find the control input of minimum effort such that all these conditions here are met. This is the condition that essentially imposes fixed time stability within this prescribed time t bar. And again, if everything can be met, then we have a solution to our original problem, what we call problem 1. Okay, you might say that, yeah, but that's a good case. How do you even know that your constraints are compatible and there will be not conflicts and you will not have to relax any of the constraints? So as we keep developing our results, we thought of adding these slack variables for the case where the solution of this QP might not be feasible. And in order to say something about the feasibility of the QP, one of the lemmas that we needed was to essentially try to see what happens in the case of disturbances that act on our system, or in other words, an intermediate result that we needed was to prove conditions for robust fixed time stability, which essentially gives us this additional result here. So nominal fixed time stability would be V dot smaller or equal than these two terms here. We added this positive term here because we needed it for the analysis of the feasibility of our QP. And as a standalone result, what essentially this result tells us is that we can find that there exist C1, C2 parameters such that if you can choose this C3 to be smaller than this bound here, then the trajectories of the system will still reach the origin within a fixed time, okay? So essentially, you can think of it as a robustness of the fixed time stable equilibrium of a system that is subject to additive vanishing disturbances if the origin of the nominal system is also fixed time stable, okay? So for vanishing disturbances, fixed time stability is not disturbed for a class of vanishing disturbances, okay? So we needed that in order to in order to prove feasibility of our QP, which now is posed in a more general and possibly useful form as adding also slack variables in our constraints. So in the control barrier function constraint and in the prescribed time control Lyapunoy function condition, in the presence of control inputs. And again, this is the fixed time bounds that need to be met. So, so the addition of these slack terms can guarantee that we can have a problem, a QP that is feasible at its time, at its x. And essentially, what we do here with this delta 1 is to relax the region of convergence, if you wish, the region of attraction for which we can reach the origin within the given user-defined prescribed time. If this cannot be met, then essentially the convergence time is going to violate the temporal aspect, but will not violate the safety. Okay, so this is in fact a paper that is currently under revision, so that's why my slides are also a little bit crude on that part. So essentially the assumption that I mentioned earlier about the structure of the system is that for the resulting QP, we have that the strict complementary slackness condition holds. And if that holds, then we can prove that the solution of this QP that I posed here satisfies that this delta 1, the optimal slack variable, remains non-positive, which means that it ensures safety. Okay, and if that is not the case, this ensures safety and convergence within the prescribed time. And this, if this is not the case, but you have a violation of your delta 1 by this term here, and remember these parameters here depend or dictate what is the convergence time, the settling time for fixed time stability. So if this condition here is met, then you conclude that the solution of the QP is safe, means that the trajectories will always stay within the safe set, and they will be converging within the prescribed time if they start within a domain D. And as you see, this domain D depends on these parameters here, okay? So from the physical intuition, if you cannot, you will not converge as fast as you might want your system to converge, but you will do converge within a finite time that is longer than what you imposed your system to be converging at. Okay, so how this is shown in an application. Back to our original example, we were thinking of problems where you have your robot maybe moving in between regions of your state space. And you can encode, if you wish, all those things with the use of STL semantics, where you might have a formula phi being true if, for example, all the state trajectories remain within the safe part of the state space. So essentially this type of always remaining safe and eventually converging no later than that time interval type of constraints or specifications can be encoded through STL formulas. So one application here, one application example is the case of a two-robot motion planning, where we have, the objective here was to have two robots starting from, one robot starts from C1 and has to move along this direction here while always staying within the square but outside the circle. And the other robot would start from C3 and would have to move counterclockwise, similarly staying within the square but outside of the circle. So at some point the robots will meet and they will have to, let's see if that plays. They will have to also deconflict as they are. So here it's where they met, and as you see here, the control is continuous, but not continuously differentiable. And you get to see that why they wait until the fact, you probably noticed the fact that they are waiting until they get to hit the next set. That is because they arrive earlier than the prescribed time that we have told them to take. So they wait until this time is met and then they move to the next set. So this would be a first implementation of how you can have also the robots connect with each other and solving a QP essentially in a centralized manner in order to avoid conflicts. How to do that for generic multi-agent systems that might be connected over generic graphs, that we don't know. It's ongoing work. And this would be, again, the results of a similar example where you get to see the paths that the robots took that are collision-free, and the fact that the violation distance, the distances are never violated, and the control inputs remain within the specified control input bounds. Okay. So as I am getting closer to wrapping up this talk, to show you some of the connections with resilient multi-agent control and some parallel directions that we are working on. So we have been working in parallel on the concept of resilient consensus and resilient consensus-based network control, where essentially the problem boils down to, and I will not describe now all the details here, that would be the topic of yet another seminar, but the idea is that when you have a network of agents and they are playing controllers that are based on consensus, the principle that they follow is that they receive information from their neighbors, and they use this information in order to play a consensus-based control, like doing some averaging or whatever. And the question that people have been studying for quite a while now is what happens if this information here that you're receiving from your neighbors involves information from malicious agents, like agents that give you wrong information, they do not want to share information, they block information flowing, and so on. So, so people have studied what would be necessary and sufficient conditions on the topology of the graph over which the agents coordinate, and they have come up with a notion of R-robustness and RS-robustness. With R-robustness, we essentially mean that a graph is going to be R-robust if you take all possible disjoint sets, and you have R incoming connections to each one of the set from agents that are outside the set. So think of it as, intuitively speaking, that you are R-robust if you are connected with sufficiently many R neighbors outside of any possible set that you might be put in. So this is a combinatorial problem, okay? So, and if you have a graph that is R-robust, then essentially a way of achieving resilient consensus is to take into account the information that you have from your neighbors, sort it relatively to your own state, and chunk out the outliers, the F highest and the F lowest values compared to your own state, and play consensus with this information. What you can show is that if your graph is 2F plus 1 robust, and you do this filtering, then the good agents are going to achieve eventually a resilient consensus, okay? So if you are essentially connected to sufficiently many agents, then you can tolerate up to F agents that might be bad without knowing who the bad agents are, okay? So why is that important? Okay, so let me move to the next slide. So the idea essentially comes down to if you want to maintain the connectivity of, or if you want to maintain the robustness of your network, then essentially you want to make sure that you stay, that you have sufficiently many neighbors, okay? So if you have disk-based models, like I am connected to those agents that are delta distance within myself, then the robustness connectivity, the robustness maintenance problem boils down to something that's very similar to the connectivity maintenance model, okay? So you want to make sure that you will not break links with sufficiently many of your neighbors. So this is where we think that it's an interesting area for putting together control barrier functions for encoding the edge connectivity, the edge maintenance, and safety at the same time, along with collision avoidance, for the case where you might have adversaries in the network. So we are working on developing these control barrier functions that are going to be robust against malicious information by making sure that they will maintain robust network structures. So I do not have the time to get into that in detail, but I guess that I'm going to leave you with this video as we are wrapping up this talk, where I'm going to show you what's happening here with our robots being deployed to achieve a formation. So what initially we do is we have them go to their respective goal locations. So They essentially exchanged goals from this initial circle. They went to the anti-dimetric point. So they resolved the conflicts with a barrier-based controller, more of a Lyapunoy-like barrier-based controller. And now what is happening is that one of those agents will start becoming as an adversary and will start sending wrong information to the others, okay? With the purpose of luring them away, okay? So you want to send wrong information because this is going to break consensus. In fact, here we have what we call physical misbehavior. This guy got stuck in the mud, but still the other guys were on a resilient network. So as you see, they do not follow him because they know that they are processing the information in a resilient manner, and they are able to filter out the bad effect of this guy. And here is one of them is sending wrong data. We just have this in order to visualize that. But the other guys do not get lured by the wrong data because they are on a sufficiently robust graph, and they keep their nominal objective, which is the consensus-based control. Okay, so where we think that fixed time would be particularly interested in is in optimization problems where you want to converge, you want to find a solution possibly within a fixed number of steps. So this is something that we are also looking in parallel. And this is my last slide. Again, putting the concepts that we are interested in into a more detailed figure here. What I am interested particularly in the next, to work on in the next couple of years would be how we can formalize these notions of how much time do I have available and how much time can I use in order to make a safe estimate, make an estimate about my environment, where learning would be also part of our investigations, and an estimate of the state of my system such that I use this within a safety critical controller that I know that I can compute, can execute within a given time, such that overall safety of the system can be preserved. So, so with that, just to acknowledge the support of our sponsors for this work, and I'm more than happy to take any questions that you might have. Thank you very much.
I have a question. You mentioned in one of your earlier slides that you had some really good work in switch systems for finite time stability. Are those papers on your website?
Yes, if not on my website, they're definitely on archive. I'm happy to send you the links, yeah.
And how about extensions to stochastic systems where like you reach like within like a certain probability? Like there's a certain probability where you hit the...
That's a very good question. We have not gotten into stochastic formulations, at least not yet. So I think that, you know, one way or the other, we cannot go always away from considering probabilistic formulations. So in principle, yes.
I'm saying because this is really relevant for a cancer treatment that I'm working on right now. So
Yeah.
Okay.
Any other questions? Well, if not, let's thank Dimitra again.
Thank you very much.